Please start the session.
So, welcome back, everybody, to session 8 on machine learning. First of all, thank you to all of you who have joined us on a Sunday. We really appreciate your efforts that you are putting in towards this course, towards this internship. Thank you for that. And I know it's a Sunday, and there have been some feedbacks that are saying that on Sundays, please keep the classes short. So, we'll try our best to do that. Okay. And let us actually get right into it then. We won't bicker around too much. Okay. So on the agenda today, basically, we have a very robust machine learning model. Okay. It is something that is used heavily in both genomics and also in the drug discovery field. Okay. So this is a machine learning model that is one of the uh, one of the better ones, I should say, and it was a breakthrough when it came out initially. So the one that I'm talking about is none other than something known as a random forest. Okay. So on today's agenda, we have the theory behind random forest. We learn how we can build a random forest and then eventually classify samples using a random forest model. After that, we will actually perform a random forest analysis using Python, okay, and scikit-learn. And we'll also learn about two other important techniques that we can do whenever we are building a machine learning pipeline. Okay. With that said, let us begin with today's lecture. So, just to give you guys some context, right? So, this is from the book that is the Elements of Statistical Learning. So, this is kind of like one of the core books of machine learning. Okay. So, according to this book, right, the authors have mentioned something, and this is something we discussed a little bit yesterday. That is, tree based models have one aspect that prevents them from being the ideal tool for predictive learning. Okay. So when we say ideal tool for predictive learning, we mean an algorithm or a framework that helps us predict stuff, right? Based on data, right? So trees or tree based models have one very big aspect that actually does not make them the most ideal tool, which is inaccuracy. And we talked about this yesterday, that decision trees often cannot compete with other models with respect to accuracy, although they are very convenient because they are very easy and simple to understand and therefore very explainable. They tend to be generally pretty inaccurate. Okay, and that is a problem, right? So basically, if you think about it, what it actually means is that they work with the data. They work really well with the data that is used to create them. So, in other words, the training data, they do really well during training, but they cannot really accommodate external data well, right? Or so to speak, they're not very flexible when it comes to the testing part, when it comes to accommodating new data and actually classifying new samples. Okay, and that leads to the major inaccuracy, right? So that is a problem with respect to decision trees by themselves. Okay, so inaccuracy during testing or inaccuracy with new data that is not the training data is the problem. So in order to solve that problem, eventually people came up with something known as random forests. So as you can maybe understand, and this is something, I mean, you can draw parallels from real life to it. A decision tree is just a singular tree, while a random forest is a collection of these trees, right? And this is exactly similar to how we look at forests in real life. Forests are nothing but a collection of trees at a particular area, right? So random forests actually combine the best of the both worlds, right? They combine the simplicity or the simple aspect of decision trees. That is, they still take care of the fact that we have to keep this model explainable. We have to make sure that it is still very simple to understand. And since they are combining several trees together, they usually lead to quite a bit of improvement in terms of accuracy as well, especially with a testing data set or external data, right? Not during training. Training, anyway, decision trees also work pretty well during training, right? But it is the testing part where they struggle. And random forests actually keep the best of both worlds, both the simplicity of decision trees as well as the accuracy of a better model like logistic regression or some gradient boosting methods, etc., etc. Okay, so that is the idea behind random forests, and that was exactly the need why random forests came to being in the first place. Okay, to solve this problem of inaccuracy with decision trees. So now that we understand the motivation behind random forest, let us understand how we can actually build a random forest. Okay, so let us go ahead and try to understand that. Okay, so this is the example that we'll take for today's class. Okay, so you can see here there are four features. The first feature is the presence or absence of chest pain, indicated by either yes or no. Second one is presence or absence of good blood circulation, indicated again by yes or no. Presence and absence of blocked arteries, indicated again by yes and no. And the weight of the person, which is a continuous numerical variable. And this is our target variable, which is the heart disease, again indicated by the yes or no. Yes will be for presence and no for absence. Okay. So the first step when we are creating a random forest is to create something called a bootstrapped data set. Okay, so we will first understand what is this bootstrap data set and how we actually create it. Okay, so for the sake of this example, again, imagine that we only have these four samples. Okay, it will be easier for us to work through the example. So let us imagine that there are only four samples here. Now, to create a bootstrap dataset that is the same size as the original, we randomly select samples from the original dataset. Okay, so here you have the original dataset. Here you have the bootstrap dataset, right? In order to create a bootstrap dataset from the original dataset, you have to simply randomly select samples from the original and put it in the bootstrap one. Okay, so there is one important detail that we have to make sure, that is that we are allowed to pick the same sample more than once. Therefore, we are going to be doing sampling with replacement. Okay, so for example, if I pick this sample, the second row, if I pick this sample and put it in this bootstrap dataset, I am not removing this sample again, right? In the second iteration, I can end up again picking this second sample randomly. Okay, so we are doing sampling with replacement. So we are sampling from this, then again replacing the sample back in the original data set as well. Okay, this is known as sampling with replacement. So this is exactly what we have tried to do here. So let us, for example, see that out of these four, we randomly chose the second one and we put it in the bootstrap dataset. Okay, now we did not remove it. We are still keeping it here. It's not like we cannot choose this again. We can end up choosing this again. Okay. Now let us say for the second random choice, we ended up choosing the first sample. So we choose it and put it in the bootstrap dataset, but that does not mean that we are removing it from the original dataset. It still remains as the first sample in the original dataset. Now, say for example, I randomly chose the fourth sample in the original dataset, and I added to the bootstrap dataset. Okay. Here is the fourth. Now, for example, now again, when I randomly choose a sample out of the original dataset, I end up choosing the fourth sample again. Okay, and this is exactly what it means to sample with replacement, right? I already sampled this as the third sample in the bootstrap dataset, but I replaced this. I took it from here, placed it here, but then again I replaced it back in the original dataset. And now at the fourth iteration, right, when I have to choose another random sample from the original dataset, I ended up choosing the fourth sample again, for example. Okay, so here you go. Now, this fourth sample is nothing but the same as the third sample in the bootstrapped dataset. Okay. So we now have a bootstrapped data set which is of the same size as the original data set, where every data point or every sample has been sampled from the original data set randomly with replacement. So what is a bootstrap dataset? A bootstrap dataset is a dataset created out of the original dataset by randomly sampling with replacement. Okay, this is the definition of a bootstrap dataset, and the definition is what tells you how to actually create it. Okay, so this right here is known as a bootstrap dataset. So now this you are seeing in terms of only a total number of 4 samples. Okay, imagine this for a total number of 400 or 4000 samples, right? You will see a lot more variation, you will see a lot more repetitions here in each of these bootstrapped data sets. Okay, can I please get a thumbs up if you have understand what is a bootstrap data set and how to create it? Okay, quite a few of you. Others, anybody else? Any questions on how we create a bootstrap data set? Okay, let us continue then. Now, in step one, we created a bootstrap data set. Okay, very simple. Now, in step two, we have to create a decision tree using the bootstrap data set, but only use a random subset of the variables at each step. Okay, so we have to now create a decision tree on this bootstrap data set, but we cannot use all the features. We have to use a random subset of features. Okay, so in this example, we will only consider 2 variables at each step. For the sake of this example, let us assume that we consider only 2 variables, right? Uh, there is obviously a way how to determine the optimal number of variables. So we will take a look at that sometime later. Okay. So for now, step two is to create a decision tree on this bootstrap dataset, but only using a subset of all the features, not all the features. Okay. Therefore, instead of considering all the 4 variables to figure out how to split the root node, if you guys remember when we were trying to figure out how to split the root node yesterday in the evening, right? We were trying to figure it out based on the Gini impurity of each of these features, right? So that is the exact same thing that we are going to do, but not considering all the 4 variables or all the 4 features. Okay. In this case, for example, we randomly select good blood circulation and blocked arteries as the candidates for the root node. Okay. We don't choose chest pain or weight as a feature that we will use in this scenario. Okay. This is again a random choice that we have made for now. Okay. Just for the sake of the example, let us assume that good blood circulation did the best job separating the samples. We already know out of good blood circulation and blocked arteries, if we were to choose which one is doing a better job at splitting, which one to put at the root node, we have to calculate something, right? Does anybody remember what that metric is that we calculate to figure out which feature to use for splitting a particular node? Do people remember? You can post it in the chat if you want, or it would be better if you actually unmute and speak. That is also fine. If you don't remember, then give me a thumbs down if you don't remember. Okay, anybody? I mean, some sort of response, people, come on. It is okay if you don't remember. Just say that you don't remember.
Dear students, what's happening?
Are you guys even here? Or did you
No,
guys just join and go back to whatever you were doing on a Sunday morning?
You want to go group wise then? Group one, anybody willing to answer?
Akshaya, Samiksha, Pratima, Siddharth, Uday. Anybody?
Don't remember. Thank you.
Okay, Pratima, you don't remember. Uday has also given us a thumbs down. He also does not remember. Okay. Anybody from group 2 remembers what we use to split a node?
Entropy and information gain.
Entropy and information gain. Yes, they are two things that you can measure, but that is not what we discussed yesterday. We discussed something else, which is the default in decision tree. Pure
Gene impurity.
gene impurity. Correct. Thank you so much, Nawaz. So that is exactly what we are going to be doing here today, right? So when I say that, for the sake of the example, let us assume that good blood circulation is doing the best job. What I mean is that good blood circulation led to the lowest Gini impurity value. Okay. Out of good blood circulation and blocked arteries, good blood circulation was the one that helped us get the lowest Gini impurity values. Okay. So let us again, for the sake of this example, choose good blood circulation as the best one and go ahead with this example. Okay. Now, once we have split whatever we need to split using good blood circulation, we have to then again figure out how to split the samples at this node, right? We have to figure that out. How do we do that? Again, just like for the root, we randomly select two variables as candidates instead of all the three remaining columns. So we have already used good blood circulation as the root. So there are three features left here, right? We again randomly select two of these three features and figure out which one is the best one in splitting this node. Again, here also we will calculate the Gini impurity of this particular node and then figure out which feature is going to work the best, whether is it chest pain or weight. Okay. So just like that, we will go ahead and build the tree, right? We'll go ahead and build the decision tree till we reach certain leaves where we have absolutely pure leaves or as pure leaves as possible. And with that, we have successfully built a decision tree as usual, but only considering a random subset of variables at each step. Okay. We did not consider all the possible variables at each step. We only considered a random subset of variables at each step, but we have built a decision tree like that. Okay. Do people understand up to here? Let's do a group wise call. Group 1, Akshaya, Samiksha, Prathima, Siddharth, and Uday. Thank you. Group 2, Varshini, Ananya. Ananya, are you here? I guess you're not here. Wahaj and Nawaz. Thank you, Nawaz. Group 3, Krishna, Sudiksha, Manaswini. Thank you. Hasini and Lakshmi. Thank you, Lakshmi. Thank you, Hasini. Group 4, we have Hajra, Sayyada, Sanjana, Nuseba, Hadi. Thank you. So, Hadi, are you the only person from group 4 today? Nobody
No, I
else?
think Saida Sidra also joined in the beginning. I don't know. Maybe she
Okay.
lost.
Okay. Sayyada, did you understand? Are you here with us?
Cyrus, even Ananya to present here. Right.
Okay.
I guess.
No worries.
Yeah.
Group 5, Lasya, Harshita. Thank you. Ramya Shri and Manaswin. Thank you. Manaswin again. I don't think Manaswin is here. Ananya has given us a thumbs up. Okay, thank you, Ananya. And now group 6, Haripriya, Tanmay. Okay, Tanmay is probably not here. Sara, Soumya, Sai Krishna, and Sadia. Okay. None of you are here then, I guess. Only Haripriya is here then, I guess. Okay. Sahiti, Sadvedi, thank you. Pallavi, Nikhil, none of you. Okay. And group 8, Praneet, Vidushi, Vedavati, Shruti. Thank you, Vidushi. Shruti, are you not here? You usually join the classes. Okay, Shruti probably hasn't joined. Shivani, Sindhura. Thank you, Sindhura. Okay, I guess that is all. So let us continue. Okay. So now we have successfully built a decision tree using the bootstrap dataset and using only a random subset of features at each level or at each decision node. Okay. So we have built this. So this is something that we have already done. This is absolutely over. It's done. Now we can go back to step 1 and repeat, right? So we make a new bootstrap dataset. So we repeat this basically. This is the first bootstrap dataset, right? We have already built a tree. We have the tree here. Good. Now we can go back again to step 1 and build a new bootstrap dataset, right? And then again, we build a decision tree considering only a random subset of variables at each step. Okay, so we can go ahead and do that, right? So if we go ahead and do that, we will have something that looks like this. We will have a collection of these decision trees, right? Ideally, you do this hundreds of times, but we have shown here only 6. But at the end of the day, you get the idea, right? So you would do this hundreds of. So now, guys, imagine the scale, right? So in this example, you guys did it with only 4 samples and only 6 trees, right? But ideally, when you are actually going to be doing it with some real data, you will end up doing it hundreds of times, 100, 200, 300, so many times. And the number of samples that you will have are nothing short of 3, 400, or even thousands, right? So imagine the scale now, and now you guys can actually try and understand and appreciate how this might help in creating a more accurate model, right? Because you are building so many bootstrap datasets. So from the same dataset, basically you are creating 100 representations. You are creating 100 datasets with different levels of variation in each dataset, right? Depending on how many repetitions are there in each of these 100 bootstrap datasets, right? You are creating different levels of variation. So your model, which is not a singular decision tree based on a singular dataset, now it is a collection of 100 decision trees based on 100 datasets with varied variations. So you are kind of making sure by doing this variation, because you're allowing sampling with replacement, what you are making sure is that you're making sure that you consider all possible variations of your data, so that whenever an external sample comes in during testing, right, it matches somewhat with some or at least one of these. Okay, that is the whole idea. That is the So in one word, if I say what random forest has that is better than decision trees, then I would say that it has generalizability. Okay, random forests are way more generalizable to any external data than decision trees, and that is exactly because of how they are built using bootstrap data sets. Okay, so that is the entire idea behind random forests, right? So this is exactly what I was trying to tell you right now, that we use a bootstrap data, we use bootstrap samples, and we consider only a subset of the variables at each step, which results in a wide variety of trees, right? So not only is the bootstrapping of the data set helping you create the variation or the wide variety, right? It is also the fact that at every step, when you are creating the tree, you are creating it based on a random subset of features, Okay, you're not considering all the features for your perusal, you're only considering a random subset of them. So that also helps you get some sort of variety into each tree, right? This variety is what makes random forests more effective than individual decision trees, right? So this is exactly what we were aiming for. We were aiming, it is already very explainable and very simple to understand, because okay, we a decision tree was a single tree, now we have 100 trees. So what? I can still tell you, if a sample comes in and if I classify it as heart disease, no, I can still tell you why, based on what features, which feature was the most important towards it. I can still tell you. All I have to do is look through 100 trees. That is fine. I can do it programmatically. It is not too difficult. So I am still preserving the simplicity of a decision tree, but I am also making this more robust and more accurate by creating variation using bootstrapping and random choice of features. Okay, these are the two most important things. One is bootstrapping and two is the random choice of features. Okay, which creates the variation. Now up to here, we have only built a random forest using our data set. Okay, so this is nothing but training, right? We have trained the model and we have built a random forest using our data set, right? Now we have to understand, how do we actually use it, or in other words, how do we test it, how do we end up actually testing it? So let us take a look at this. Okay, so for example, if a new data comes in like this, say with chest pain as yes, good blood circulation as no, blocked arteries as no, and weight as 168, and we have to classify using the random forest we built whether this person has a heart disease or not. Okay, so what we can do is, say for example, we run the data down the first tree we made 6 trees, right? So we run the data down the first tree, we have all the information here that we need to actually follow the path that it takes, right? So we follow the path, say for example like this, and it takes us to the point where this particular tree says yes to heart disease for this sample. Okay, and then we keep a track of that here. Okay, that heart disease yes is 1, no is 0. Now we do the same thing with the second tree that we have built. Okay, say for example the second tree also says yes. Okay, now we repeat that for all the trees that we have made. We can do that, right? And say for example, this is kind of the final score where 3 of the trees gave us a yes answer and 1 tree gave us a no answer. Okay, so then we do it. So we totally built 6 trees. So this is in the fourth tree, right? Now for 5 and 6 also, say for example, it gave us a yes, right? So for the 6 trees, only 1 tree tells us that this sample uh, should be denoted as a heart disease no, and 5 trees tells us that this sample should be assigned to heart disease yes, right? So in this case, yes has received the most votes. Okay, so we will conclude that this patient has a heart disease and we will put a yes here. Okay, this technique is known as majority voting, and this is exactly how random forest handles classification problems. So again, this is not something that is new to you guys. We already discussed this in the context of decision trees yesterday, right? We already discussed this in the context of decision trees yesterday, and this is the same concept. If you have ended up building 100 trees, right, you will run the data down each one of those 100 trees and check whatever vote you are getting for the classification, right? Whichever is the majority vote, you choose that class for this particular sample, and that is how you end up classifying it. Okay, this is known as, so basically bootstrapping the data, right? So if you guys remember, we created bootstrap data sets, right? So bootstrapping the data plus using the aggregate to make a decision. Here we are using the aggregate to make a decision, right? We are using the decision of 6 decision trees together, aggregating them together to get a single decision, right? So whenever we are using a model that uses bootstrapping as well as aggregation to actually give you a decision or to actually give you a prediction, we generally call them, we generally put them under a class of models or techniques known as bagging. Okay, bagging, the B comes from bootstrapping, and the agging comes from aggregation. Okay, so we generally put them under bagging. Okay, and as you all would have already guessed, with respect to random forests, again, the majority voting is the method by which it solves classification problems. But for regression problems, again, what do we do? If you guys remember, in decision trees, at each leaf in a regression problem, at each leaf there would be continuous variables or numbers, right? There would be a selection of numbers and not exactly your discrete decisions or options, right? There would be a continuous numbers, right? So here also, in each of these trees, in each of these leaves, there would be numbers. You run the data down each of these trees and you get the average from each of these trees. So each tree will help you get one number, right? Each tree will output one continuous numerical value to you, and all you have to do finally is find the average of that one continuous numerical value. And again, this is more robust than a single decision tree, because a single decision tree was giving you only one aspect, right, for quite a bit. So say for example, there were 5 samples which were situated here, 5 target numbers here, right? If a new sample comes in which is very similar to these 5 target numbers, right, for all of those samples that come in which are very similar to these 5 target numbers, the value for them would be the same, which is the average of these 5 target numbers, right? But you don't really want that. You want variation. You want variation even in a regression setting, right? So this guy might give you some form of an average, this guy might give you some other average, this guy gives you some other average, this guy gives you some other average, etc., etc. Now you take an average of these averages to get even more closer to your actual regression value. So that is how these things work with respect to a regression setting. Okay, and with respect to a classification setting, as we all know, we use the majority voting approach. Okay, so this is exactly how we figure out, or how we test our random forest, how we run down unknown data through the random forest. Okay, so do people understand up to this part? Can you guys please confirm with a thumbs up? Okay, quite a few of you. I think we're good to continue then. Okay, now let us actually try and understand how we can actually validate our random forest, right? So how we actually know whether it is performing good or bad. Okay, let us try and understand. Okay, so remember guys, in our bootstrap data set, we allowed duplicate entries, right? We did sampling with replacement, so it is absolutely natural for us to have duplicate entries in our bootstrapped data set. Okay, as a result, what happened, this particular data point, right, this particular sample was not included in our bootstrap data set, right? Because this is sample 1 in bootstrap dataset, this is sample 2 in bootstrap dataset, and this is both sample 3 and both sample 4 in our bootstrap dataset, right? So this sample did not get picked randomly, right? So this is not part of the bootstrap dataset, right? In other words, this particular sample will be known as the out of bag dataset. Okay, this particular sample is known as the out of bag dataset. Please note here that we are only using 4 samples for our example, right? If our dataset was much larger and there were hundreds of thousands of samples, we would actually have an entire we would actually have an entire collection of samples which were not part of the bootstrap dataset, right? We would, and that is why we are calling, even though this is only a single sample, we are still calling it an out of bag dataset, because uh, it is still a dataset, but the dataset only contains 1 sample. Okay, and that is because the original dataset itself has only 4 samples. right? If you have hundreds of thousands of samples, your out of bag data set would actually contain quite a lot of samples, right? Because there would be quite a lot of samples that were randomly not chosen, and that is absolutely fine and absolutely valid. That is what happens, right? So this guy is known as the out of bag data set. Okay. Now what we can do is we can run it through the forest that we have built. We can run this out of bag data set. We can run it through and see if it correctly classifies the sample as no heart disease. Remember, for this, we already have the information, right? We already have the information that it does not have a heart disease, this sample, right? So we can try and run it through our random forest and see that whether it classifies this correctly or not. Now remember, this is an out of bag data set. So this did not, so the model did not actually encounter this data, encounter this particular sample when it was going through the training. So then this is not somewhere where the model can actually cheat and memorize, right? It has to do it correctly for us to know, right? So let us see what happens. Say for example, we run it down the first tree, right? And in this case, the tree has correctly labeled the out of bag sample as no. Okay. Then we run this out of bag dataset through all the other trees that were built without it. Okay. So now if you guys remember, this is the first tree that we built, and this was built using this particular bootstrap dataset that did not have this sample. Okay. So now this is an out of bag data set for the first tree only. Okay. For the second tree, this might have been actually used to build the second tree. We don't know that. But for the first tree, it was not used. So this is an out of bag data set for the first tree only. So we run it down that particular first tree. Then we also run it down all the other trees that were built without it, right? So then we run it down all the other trees as well. For example, this tree incorrectly labeled the out of bag sample as yes. Okay. And these trees, for example, labeled the out of bag sample as no. Okay. Now, if you think about the classification of the out of bag sample, right? We had three no's, right? We had three no's and one yes, right? So the original tree gave us a no, this guy gave us a yes, and these two also gave us a no. So we have three no's and one yes. Since the label with the most votes wins, it is the label that we assign to this out of bag sample, right? So we will assign the no label to this particular out of bag sample, and in this case the out of bag sample has been correctly labeled by the random forest. Okay, so this is exactly how we do, and we actually validate the accuracy of random forests. Okay, so not only do we build the random forest, we now know how to build the random forest, right? The first step is to create a bootstrapped data set, right? A bootstrap data set is a data set which is created out of the original data set, is of the same size as the original data set, and has samples from the original data set but with replacement, right? Now what do? We build a decision tree using this particular bootstrap dataset, right? And at every decision point or at every node, the choice of features is a random subset out of all the features. So we don't use all the features, we only consider a random subset. Okay. So these two aspects, which is bootstrapping of the dataset as well as choice of a random subset of features at every decision node, helps us create variety, right? We make hundreds and 200 and 300 such trees, which are of all kinds of variations, right? So it gives us variety, right? Then we also saw how we can use a random forest, right? In a classification setting, all we have to do is run the data point, the unknown data point, through each and every one of these decision trees in the random forest and take a maximum voting approach, right? In case of a regression problem, we again run it down each and every decision tree. Whatever value is outputted from each and every decision tree is kind of uh, it is kind of kept hold of, and then we perform an average on top of that. So it is an average of averages in case of a regression setting, right? And finally, we also saw how we can actually estimate how well or how bad our random forest is doing by estimating its accuracy. And how do we do that? We do that using samples which were left out of our bootstrap dataset or our out of bag dataset. Okay, so we use the out of bag dataset, classify those samples, and since we already know their outcome because they were obviously known samples, they were part of the dataset originally. Since they were, since we already know, we can obviously assess whether our model has predicted or classified them correctly or not. Okay, so this is what we have learned up to here, up till now. So let us do a quick group wise call to make sure that everybody right now is on the same page. Okay, so let's start with group 1: Akshaya, Samiksha, Pratima, Siddharth, and Uday. Okay, thank you all. Group 2: Varshini, Ananya, Wahaj, and Nawaz. Have you guys understood? Thank you, Varshini and Nawaz. Okay, I don't think Ananya, you were here, right? Have you been able to understand up to here? Yes. I think Ananya was here. Okay, Ananya, if you are having some troubles, please try to fix it and give us a thumbs up if you can. Okay. Um, Group 3, have you guys able to? Are you guys able to understand? Krishna, Sudiksha, Manaswini, Hasini, and Lakshmi. Thank you. Group 4: Hajra, Sayyida, Sanjana, Nuseba, and Hadi. Okay. Group 5, we have Lasya, Harshita, Ramya Shri, and Manaswini. Thank you, Harshita. Thank you, Ramya Shri. Group 6: Haripriya, Tanmay, Sara, Soumya, Sai Krishna, Sadia. Nobody is here. Okay, no problem. Group 7: Sahiti, Sadvedi, Pallavi. Thank you, Sadvedi. Pallavi and Nikhil. Okay, not a lot of you here. Group 8: Praneeth, Vidushi, Vedavati. Thank you, Vidushi. Shruti. Thank you, Vedavati. Shruti, thank you. And Shivani and Sindhura. Sindhura, you have also given us a thumbs up. Thank you. Shivani, I don't think you are here. Okay, no worries. Okay. So we are all on the same page. Great. Okay. Now let us talk about a few more pointers with respect to random forests. Okay. But now we know how to build a random forest, how to use a random forest, and how to basically estimate the accuracy, right? Now let us actually talk about how, I mean, we did skip on a few things, right? When we were building a random forest, let us actually address them, right? So you guys remember when we built our first tree and we only used two variables, right? To make a decision at each step. We did that, right? When we built the first tree for the root node, we said that, okay, let's randomly choose good blood circulation and blocked arteries in order to compete for the root node, right? We said that, right? And we actually built the tree using that, right? Now we can compare the out of bag error for a random forest built using only two variables per step. Okay, this, let us see what we mean. To a random forest built using three variables per step, right? So at this point we have said that, okay, we will only use two variables or two features randomly at each step, right? And we will calculate the out of bag error. We can do that, right? by calculating the out of bag classification, right? And then figuring out whether it has classified it correctly or not. So we can figure out whether it has made an error. So we can calculate the out of bag error, right? So imagine this. The first scenario is where whenever you build a decision tree as part of a random forest, at every decision node, you choose only two out of the available features. Okay, randomly two out of the available features. Okay, now I can also have a scenario where I have a data set and I will build a random forest. So within that random forest, each decision tree will be built using three variables randomly out of all the available features, right? That is absolutely possible, right? So apart from this, we can also test out a bunch of different settings and choose the most accurate random forest, right? So ideally, obviously, you will not have only like 3 or 4 features. You will have way more features, right? For example, with respect to the diabetes dataset that we have kind of come across, right? We saw how we have 8 features there, right? So I can choose as many features as I want, right, to be used or to be within the candidature of each decision node in each decision tree. Okay, I can choose that, and this is something which is a hyperparameter, and this is something that you will use. Okay, this is a hyperparameter that you can tweak and you can check, and what it does is every time it builds a random forest using that many features chosen randomly out of the entire set, right, out of the entire set of features, it builds the random forest, creates it calculates the out of bag error, and the choice is made based on the highest out of bag accuracy. Whichever number of features, say for example 2, 3, 4, 5 number of features, right, per step, right? So it's not like that we are only using those 5 features and not using the rest of the features at all. No, right? At each step, we will randomly choose 5 features out of the entire set of features to compete for that decision node. Okay. Then again, at each step, in another scenario, we will randomly choose 3 features out of the entire set of features to compete for that decision node. Okay. It's like that. And we can test out different settings like this and eventually choose the most accurate random forest. Okay. So in other words, we build a random forest, then we estimate the accuracy of the random forest using out of bag error, and then we change the number of variables used per step. Then again we build a random forest, again estimate the accuracy, and we keep doing this a bunch of times, and then finally we choose that random forest which is the most accurate in terms of classifying the out of bag error. Okay, and finally we choose that random forest which is the most accurate in terms of classifying the out of bag error. Okay, do people understand? Can I please have a thumbs up if you guys understand up to this part? Okay, you want me to repeat. Okay, so let me actually take you back to the slide so that you can understand. So if you remember, right, in the first instance, right, when we built that random forest with those 6 decision trees, we decided that we will only use 2 variables per step. What this means is that at every decision node, we will randomly choose 2 out of the 4 variables, right? And those are the ones who will compete for that decision node. Therefore, for the root node, we randomly choose these 2 variables, right? And these 2 competed, and we ended up with good blood circulation here, right? Then again, for this particular decision node here, we randomly chose blocked arteries, right? Out of blocked arteries and weight, for example, right? We randomly chose blocked arteries. Then again, for this decision node here, we chose, say, for example, chest pain, out of chest pain and good blood circulation, right? So at every step, we are randomly choosing 2 variables or 2 features out of the entire set of features to compete for that decision node, right? Now, I can also do this using 3 features to compete for a single decision node, right? For example, at this stage, instead of only choosing randomly good blood circulation, blocked arteries. I chose good blood circulation, blocked arteries, and weight because I have set this value to 3, right? And then now these 3 compete amongst each other to figure out which one will form the root node. Okay, so this is a completely different random forest. We build an entire random forest. That is to say, we build a collection of said decision trees using only 2 variables per decision step, right? Then we build again another random forest, right, with only 3 variables per decision step, right? We can do that. We can absolutely do that, right? Now we can compare these 2 random forests, the one which is built using 2 variables per step and the one which is built using 3 variables per step. How do we compare them? We can compare them by actually performing out of bag classification and then figuring out how well or how bad it did in terms of accuracy with respect to the out of bag data set, right? Therefore it is in our hands to choose which one is going to give us a more correct classification and which one is not, right? Say for example, 3 variables per step at each decision step in a random forest is giving you a better classification result, so you will stick to 3 for your final model, right? This is exactly what this is, right? And again, this number, this 2 or 3, that is how many variables that you want to use in each step. This is a hyperparameter that you can optimize, and we'll see exactly how we end up optimizing it in today's class, but this is a hyperparameter that you can optimize. Hadi, is that clear now, or do you still have questions? Please feel free to ask. If you still are confused, I can go again. Not a problem. Okay, it's clear. Okay. Anybody else? Any more questions on how we build a random forest, how we test a random forest, how we try out different random forests and choose the most accurate one? Bagging, bootstrapping, out of bag data set, etc., etc. People understand? Can you please give me a thumbs up if you are all on the same page? Okay, only 4 or 5 of you. What about the rest? You people also understand? Come on, at least 2 or 3 more of you. Give me a thumbs up, guys, please. Okay, thank you, Uday. Thank you, Samiksha. One more. Come on. Okay, no worries. If you have any questions at any point, please feel free to raise your hand or put it in the chat. I will answer it. Okay, no worries. And with that said, this is what I have with respect to the theory of random forest. We now know how to build a random forest, estimate the accuracy of a random forest, and also use a random forest on external data. Okay, so with that, we understand how random forests work and how they actually solve the inaccuracy problem that was there with decision trees while preserving the simplicity and the explainability feature of decision trees. Okay, that is really important for us to understand, and we have done that. So with that, we can stop here today for the theory, and we will begin with the lab. Okay, so what I want you guys to do now is again go to the scripts folder of your Google Drive and download this particular .py file and place it in the PyCharm projects folder. Okay, once you have done that, we can start. Okay, so I'll give you guys again a couple of minutes. We'll start at exactly 11:07. Okay, so let me actually show you guys. This is the script. Okay, once you have installed, once you've downloaded it, just go ahead and open it in PyCharm and we can start. Okay. Okay, can we please have a thumbs up from you guys if you have been able to download the script and place it in the correct directory? Okay. So let's go group wise one more time. Akshaya, Samiksha, Pratima, Siddharth and Uday. Okay. Group 2, Varshini, Ananya, Wahaj and Nawaz. Okay, thank you. Group 3, Krishna, Sudiksha, Manaswini, Hasini and Lakshmi. Yes, thank you. Group 4, Hajra, Sayyada, okay, Sanjana, Nuseba and Hadi, thank you. Group 5, we have Lasya, Harshita, Ramya Shri, thank you, and Manaswin. Okay, no worries. Group 6, Haripriya, Tanmay, Sara, Soumya, Sai Krishna, and Sadhya. Okay. Group 7, Sahiti, Sadvedi, Pallavi, and Nikhil. Not here. Okay, no worries. And group 8, Praneet, Vidushi, Vedavati. Thank you. Shruti, Shivani, and Sindhura. Okay. Okay, so I guess most of you have been able to do it. So let me share my screen and we will start with today's random forest lab. Okay. So go ahead and open the script in PyCharm and then we will start with our execution. Okay. So again, as you can see, the top portion here is nothing but all the import statements that we need, right? And today we are going to be using the random forest classifier. Okay, it is part of the ensemble library of scikit-learn. Okay, ensemble basically is basically are the class of models, right? It falls under those models which use a collection of different models to actually give you the answer. Okay, and if you think about it, uh, random forest uses a collection of decision trees, right, to give you the answer. So that is why it has been kind of put under the ensemble library. Okay, and apart from that we will also learn about something known as randomized search CV and grid search CV with respect to model building. Okay, these two are the ones which actually help you perform hyperparameter tuning. Okay, so just like the previous classes, the first few lines are common to all, right? We'll load the data set, right? And we'll set the working directory, load the data set, figure out what are the features, right? And then create the X and Y matrix followed by the trained test split. Okay. So I will directly put a breakpoint here at line number 33 and I will go ahead and hit the debug button. So let it run. Just give it some time. Okay, so once it has run till here, you can see now this is going to be another new line for us. So this is where I define the model object. So we are going to be using the random forest classifier function, obviously. I have set a random state here for reproducibility and I am using another parameter here which is OOB score or the out of bag score, and I have set it to true, which basically means that use the out of bag score to judge and decide which particular random forest or which particular hyperparameter works the best for you. in terms of in terms of how many features to use to split per node, right? So it will do that. It will figure out the classification based on the OOB score. Okay. Then again, it is all the same with respect to all the other models that we have done. We first fit on the training data, and then finally we test using the testing data. Okay. We predict using the testing data. So after that, we will get all of these scores, right? For example, for the OOB score, what we actually have to do is for the OOB score, what we actually have to do is, so this particular variable only will return this particular value under this guise, which is OOB underscore score underscore. So we can directly print that after we have done, after we are done fitting the model. Okay. And then just give me a second, guys. I'm having some issues over here. Just 1 second. So sorry, guys, for that. Really apologize. Let us continue. Okay, so as I was saying, when you actually fit the model and you are done with your predictions, right? The model automatically creates the OOB score variable here, and you can access it using OOB underscore score underscore. Okay, so you don't have to calculate it explicitly again, like in the case of accuracy score, confusion matrix, F1 score, or precision score. Okay, these are again the same as we have been doing for the past lectures, right? We give both the y test and the y pred. So our y pred is what the model has predicted, right? This is y pred, and y test is the ground truth of the test variable, of the test, basically the testing data set, right? So we will go ahead and define the model, then followed by fitting the model. Okay, so now we will do our predictions. Okay, then we can calculate the OOB score. You can see that we are getting an OOB score of 0.7524. Not too bad. Okay, so this is very similar to the accuracy score, right? So a 75% score accuracy, right? Now again, accuracy, it is obviously a bit lower because again, this is done completely on unseen data for the model, which is the testing data, right? This is our confusion matrix. Not too bad. We are making 43 errors. So decent, not the worst, right? and then we have the precision score and the F1 scores. Okay, so this is the basic model without any sort of pre-processing in this particular random forest model. Okay, this is without any sort of pre-processing. Now let us actually standardize the features. Let us actually perform some pre-processing and check what might happen. Okay, so let us first define the standard scalar feature scaling method, right? We already discussed this in the lecture that we did for linear regression, if you guys remember, right? So let us use standard scalar. Then we'll fit using the training data. And as you guys remember, we transform it both on the training and the testing data, right? So we will go ahead and do that. Now that our features are scaled, we might expect some better performance, right? So that is what we are going to test out here. Let us actually see if that is the case. Our model is fitting. If for some reason there are two fit statements here, you don't really need two. One is more than enough. Okay. So we will then make our predictions and then let's see if there are any improvements, right? So the OOB score is pretty much still the same. The accuracy is also pretty much still the same. So not too much improvements, right? And this did not really do a lot here. Okay, so what we can do now is we can also try out some other scaling methods. Say for example, instead of standard scalar, we can also try out our min max scalar. So let us go ahead and try it and see whether it is making any difference or not. Okay, so I'll remove this breakpoint, go in here and replace this with the min max scalar. Okay, always remember to put the bracket after it because it is a function, right? Then we can directly put a hyperparameter here at line number 59, remove all the hyperparameters before and go on and run this particular model. Okay, so this is running. Let's just give it some time. Okay, so again we see not too much of a difference, right? Not too much improvement or deterioration, so that is absolutely fine. uh, Basically feature scaling is not doing a lot in terms of random forest, right? And that kind of actually makes sense, right? Because in a random forest, all you're doing is you're using a collection of decision trees. Decision trees are something that are technically scale agnostic if you think about it, because anyway you're making decision nodes, right? You're making decision nodes and you're putting raw values there, right? So the scale of the value should not matter because you're working with ranges here, not discrete values. You're working with ranges here, so the scale of it does not really uh, affect too much when you're working with random forest or decision tree models, right? Therefore, even if you guys remember, even in yesterday's lecture when we used decision trees, right, scaling did not really change the accuracy too much, right? We still ended up having the same accuracy because at the end of the day you are using ranges as part of your decision points, right? So the range, the scale of the range does not matter, right? It will translate to a different scale, but the range will still remain the same. Okay, so that is why scaling does not really help too much with respect to models like random forest and decision trees. But then again, this differs from data to data. Okay, so it is always advisable to test it out, but in most cases scaling is not something that helps a lot with random forest models. Okay, so now that we understand that, let us actually, so we have built, we now know how to build a random forest model. We now know how to predict, how to print the OOB score and whatnot for the random forest model. Okay, so if everybody has followed up to this part, can you please give me a thumbs up? Yes. Okay, People have followed up to here. Okay, good. Now let us understand something that we have been talking about for quite a while now, which is hyperparameter tuning. Okay, so hyperparameter tuning is the technique by which I can actually fine tune all of these hyperparameters that I have. Right, there are several for each model. There are several hyperparameters which are available, and as analysts and as machine learning people who perform machine learning analysis, right, what we have to do is we have to try and test different values of these hyperparameters in combination with each other to figure out the best possible combination. Okay, that is literally what we have to do when we are building these models, right? Now, in order to do that, obviously, we have to first define something known as a hyperparameter grid. Okay, so if you guys remember what a hyperparameter is, right? You guys remember? Can anybody tell me what a hyperparameter is? It has a very specific feature. It is a parameter that is it is used to improve the model. Absolutely, that is correct. Any parameter helps you in making better predictions, so that is there. But what is the difference between parameters, which are those theta values that we saw in regression, right? And the difference between that and hyperparameters? What is something which is unique about hyperparameters? Uday, you have said that tuning. Yes, so do you mean to say that we can tune hyperparameters? Is that what you're trying to say? You're saying used in validation. Okay, used in validation. But yes, Nawaz, exactly. So make a note here what Nawaz has said, guys. The unique thing about hyperparameters and how they are different from the other parameters is that hyperparameters are our control. The rest of the parameters, if you guys remember those theta values, they are actually learned, right? They are actually optimized and learned during the training process. Hyperparameters are what we set. So it falls on us to try out different values of these hyperparameters to figure out which combination of them works the best for my data and for my scenario. Okay, very good, Nawaz, very good that you remember. Okay. And Pratima, you're also correct that they can vary, right? But that is not a unique feature about these hyperparameters. Your other parameters can also vary, right? The parameters with respect to your features, they can also vary. Okay. Okay. So now let us actually see how we can do this hyperparameter tuning. Okay. So the first and foremost thing that we have to do when we are performing hyperparameter tuning is to define something known as a parameter grid. The way we define it is by defining a dictionary where the key of the dictionary is the name of the hyperparameter and the value is a list of all the values that I want to try out. Okay. So here you can see these are my keys, which are strings, and the values are lists of all the values for that parameter that I want to try out. Okay. For example, with respect to random forest, we are going to be carrying out hyperparameter tuning for all these parameters. Okay. Say, for example, the first parameter that we have is the n estimators parameter. So these n estimators parameter basically stands for the number of trees that we will build in our random forest. Okay. So if you guys remember in the theory example, we built 6 trees, right? And we told them that you would ideally do that hundreds of times. And this is exactly what that means. How many trees should I build in my random forest? 100, 200, 300, 400, 500. I will try out all of these. Okay. Now max depth stands for the maximum depth of a single tree. That is till how much has the tree particularly expanded. Okay. So for example, let me tell you guys this. Let me take you back to the slides just once. For example, this tree, right? This tree at the top, this tree has a depth of 3. Okay. So this tree has a depth of 3 because there are 3 levels to it. Okay, this tree has a depth of 3, right? Similarly, these two trees as well. If the tree would have ended somewhere here, it would have a depth of 2. So 1 and then 2. So this is nothing but the depth of a tree, or how deep or how much towards the bottom are you going. Okay. And if you think about it, if you are going till the very end, right, all the nodes in the tree will be nothing but pure leaves, right? That is when you stop, right? When all of them are nothing but pure leaves, right? So this is what this is. So when I say the max depth here, what I mean is how much depth do I want this tree to go to, right? And if I have put none, that basically means that you please expand the tree up to the point where each and every leaf is pure. Okay, that is what this means. Okay. Min sample split is a hyperparameter that denotes how many number of samples is a minimum requirement for you to split a node. Okay, say for example, today I might decide that unless and until there are at least 10 samples in a node, right, you don't need to split it, right? So for example, even if there are 5 samples, or even if there are 2 or 3 or 4 samples in a node, right, you don't need to split it. Okay, you can let it be. Although that leaf will be an impure leaf, right, it might be an impure leaf, that is fine with me. Okay, sometimes these things also help. And if you think about it, right, if you make every decision tree till the very end where every leaf is pure, you might end up doing something which is not at all recommended. Okay, can anybody guess what I am trying to hint at? Right, if you build every decision tree in the random forest till the very end where all the leaves are pure, you might end up doing something to your data that is not at all recommended. You have to kind of balance something. Does anybody remember? Can anybody guess what I'm trying to hint at? Do people remember the term overfitting? No, not test and training sampling. Not that, Hadi. Do you guys remember the term overfitting? Can you please give me a thumbs up if you remember the term overfitting? Okay, Hadi has given us a thumbs up. What about the rest of you? None of you remember overfitting? Pratima, thank you. Others? Memorization. Yes, kind of correct, Hadi. So overfitting is when your model is kind of, as Hadi said, memorizing your data set, right? It is not actually learning the patterns. It is learning the noise in your data set as well, right? And when you end up creating decision trees till the very last leaf where every leaf is absolutely pure, right, you might end up memorizing the data, you might end up overfitting your data. Okay, so that is why it is always good to try it out. And these are basically features: max depth, min sample split, and then again min sample sleeve. These are all features that help us prevent overfitting. Okay, so min sample split is the minimum number of samples required to split a particular decision node. Okay, min sample sleeve is the minimum number of samples required at a leaf node. Okay, so for example, I can choose to have at least 4 samples in a leaf node, right? Although it might lead to an impure leaf, right? I can choose to have it just for the sake of preventing overfitting. Okay. So again, these are choices that we make. Also, these values that you see here, they are not in any way exclusive. Okay, they are not in any way, I should say, the absolute all that you should use. No, you can try out any value you want under the face of this planet, right? I have done this based on the general tutorials which are available on their documentation pages. Okay, so and the general consensus that people use. Okay, so you can use other values as well. You can use more values as well. Okay, so I have used only 3, 2, 5, and 10. You can use 2, 3, 4, 5, 6, 7, 8, 9, 10 till that does not matter. Okay, you might end up getting something better. Okay, so these are not at all complete by any not by a long shot. Okay, they are just representative of what you can do. Okay, this feature or rather sorry, this hyperparameter max features, right, this stands for the number of features you should consider when looking for the best split. Or if you guys remember, this is what we discussed. This basically is the hyperparameter that tells your model that use this many features at each decision step, right? Choose out randomly, choose a subset of this many features at each decision step. Okay, this is that one, right? And you can put any value that you want here. And basically there are some values which are part of the documentation. I will show you guys, right? That is, you can use the square root of the total number of features, you can use the log2 of the total number of features, etc. Okay, and bootstrap I have set to true here because I don't want this to vary. I want it to always carry out a bootstrapping. Okay, I don't want it to vary because that is really the crux of the random forest, right? Without bootstrapping, a random forest is not really a random forest. Okay, so now that I have defined this parameter grid, I will go ahead and run this. Okay, now this parameter grid is a dictionary which has been created. Now what I will do is I will first and foremost initialize my classifier, which is RF model and the random forest classifier, right? I will again put random state to 42 for reproducibility, and then I will use the randomized search cross validation function. Okay, so what this randomized search cross validation function will do is it will create random combinations of this particular set of hyperparameters and test my model and tell me which one works best. Okay, so when I say random combination, say for example in the first scenario, it picks n estimators as 300, max depth as 20, min sample split as 2, min samples leaf as 2, and max features as log 2. Okay, all of this has been picked randomly. This is one iteration. It will build a model using these hyperparameters. Okay, in the second iteration it will again create a random a random combination of all of these hyperparameters. In the third iteration it will again create a random combination of all of these hyperparameters, and it will keep doing that for as many times as I have told it to do, right? So in this randomized search CV, this is exactly why it is known as randomized search. So it is randomly searching through your parameter grid to look for the best parameters, right? It is not creating every last possible combination. It is not creating every possible combination. It is only creating random combinations based on how many number of times you have asked it to do it. Okay, so say for example, these are those parameters that control it. But before that, let us understand, when we say we have to give the estimator parameter to it, in the estimator parameter, all we have to do is give the model variable where we have defined the model, and the param distributions parameter will take the parameter grid. Okay, after that, n iter equals to 20 basically means that the number of iterations is going to be 20. So what this means is that I want it to test out 20 random combinations out of this parameter grid. Okay, there are a whole of a lot more combinations of parameters which are going to be available through this small parameter grid. You can create so many combinations, right? But then again, what happens is sometimes if you are trying out every single combination of every single hyperparameter, it becomes really cumbersome for everybody. It also sometimes becomes too heavy for your computer, and it takes up a lot of time to run. Okay, so people usually settle for randomized search CV. Okay, so this will do it for randomized search CV or cross validation, randomized search cross validation, right? And it is not like it will do it only 20 times with random combinations once each time. No, it will perform a 5-fold cross validation because I have put CV is equal to 5. I could have put 10, I could have put 15, etc., and it would have done that much amount of cross validation. So for each of these 20 iterations, right, with a unique random combination of hyperparameters, it will perform a 5-fold cross validation and optimize based on the accuracy score. Okay, that is what this scoring is equal to accuracy stands for. You can also put the other metrics here, which is precision, F1 score, sensitivity, specificity, etc. That is absolutely up to you. It all depends on the requirements of your model. Okay. Verb random state, as we all know, is for reproducibility purposes. Verbose is basically a parameter that you will see. It is a common parameter in a lot of Python functions, and it is a parameter which basically kind of controls how much of text and how much of messages you want it to print in the console when running all of this. Okay, that is what this is for. So verbose is equal to 2 is good enough. You will see that will print some necessary messages that will actually help you understand what is going on. So that is fine. So let me go ahead and define this random search object. Once I have done that, I can now fit, or I can now train my data onto it. Okay. So once I hit this, you can see that this has printed that, okay, fitting 5 folds for each of 20 candidates, totaling 100 fits, etc., etc. And it is this, these are all the cross validations, and these are all the kind of, so you can see it is doing, it will print this guy 5 times now, right? Because it is doing a cross validation of this particular combination of features 5 times. Now it will print a new combination of features. Let's see. So this is going to do it 20 times basically. So 20 times 5, which will be a total of 100 fits. That is what you will see. See here, now it has changed the combination of features and it has randomly chosen something. So all of these will take some time, right? While it runs, I will show you the other one here. Okay. So this is something known as the grid search CV. Okay. So just like randomized search CV, before it also, you have to first define a parameter grid, right? And the difference between grid search CV and randomized search CV is that grid search CV searches not only for randomly possible combinations, it searches for each and every single combination possible. Okay, so for each and every combination possible, no matter how many they might be, it will perform 5-fold cross validation, optimize for accuracy, and then give you the results. Okay, that is what grid search CV does, and this is something that usually takes a long time. You can see a total of 100 fits with only 20 possible combinations is taking up so much time, right? So you guys can kind of imagine how much more time it would take for grid search CV to run, right? Because grid search CV will look for every possible combination, and on every possible combination it will do 5-fold cross validation. So that will automatically take a lot of time. Okay, so this is the difference between randomized search CV and grid search CV. Okay, so after randomized search CV is done doing the training, what we can do is we can print the best hyperparameters that we got to know. So it will print the best combination of hyperparameters. Okay, so in order to do that, we can use the best underscore params underscore variable here, which will give us the best combination of hyperparameters, right? And now our idea is, now that we have figured out which is the best combination of hyperparameters, we can actually use that, right? And we can define it as the best underscore rf underscore model, and we can use that to actually train and test our data. So what do we do? So we put random search, because random search is the one that we had defined here as the randomized search CV object, right? And on top of that, we use the object which is the best estimator. So this guy, best params, prints the combination of best hyperparameters, and best estimator kind of loads the random forest classifier using the best parameters. Okay, so this line is the same as writing this line, but with all the parameters written here inside the bracket. Okay, that is what this line will do. Right? And then we can do our all sorts of the we can print the OOB score, we can do the prediction using the best RF model. Training has already happened here, so we don't need to train again, and we can use the predictions, etc., etc. And then we can actually print here the model performance with our best hyperparameters. Okay, so this is what this will do. Similarly for grid search CV as well, it is the same thing. You can print the best combination of parameters here. So obviously this is the one which will always give you the best result, grid search CV, because it uh, iterates through, or it goes through all possible combinations, right? So there is nothing it misses. So obviously this will give you the best result, but this usually takes up a lot more time than randomized search CV. You can see the randomized search CV only is taking up quite a bit of time. Okay, and obviously this is because we are doing it on our laptops, so it will take some time. That is absolutely fine. If you actually do it on high performance computing clusters or some nice GPU server, you actually don't need to spend too much time, and it will run like that in a flash. Okay, so yeah, but still, since a lot of people still use their laptops and still use their personal computers to actually run these machine learning models, right, randomized search CV is kind of a way out for them. Okay, I don't recommend you guys to use grid search CV because I'm not sure as to the specs of your laptops. So I mean, I don't know, but you might end up crashing your laptop if the specs are not too high. So I don't recommend using this, but then again, you can try. Even if your laptop crashes, so what? Just make sure that you don't lose out on any stuff. Save everything beforehand and then try it. So even if it crashes, all you have to do is restart your laptop and you're good to go. Okay. So you guys can try it out, right? And then the rest of it is pretty much the same as we did for the randomized search CV. So with that, let us wait for a while till randomized search CV finishes. And as this goes on, let us actually go through group wise one more time to actually see if we are all on the same page. So if you have been able to follow till our particular execution, and if you have understood how to perform hyperparameter tuning and how to actually set up what randomized search CV does, right, what each parameter meant and how are we actually optimizing for accuracy. If you have understood all of this and if you have been able to follow and execute the script along with me, please give me a thumbs up. Group 1, Akshaya, Samiksha, Pratima, Siddharth and Uday. Okay. Group 2, Varshini, I already saw you gave a thumbs up. Thank you. Ananya, Wahaj and Nawaz. Thank you. Group 3, Krishna, Sudiksha, Manaswini, Hasini, and Lakshmi. Okay, thank you. Group 4, Hajra, Sayyeda, Sanjana, Nuseba, and Hadia. Yes. Okay. Group 5, Lasya, Harshita, Ramya Shri, and Manaswini. Group 6, Haripriya, Tanmay. Thank you, Pallavi. Sara, not here. Okay. Sai Krishna, Sadia. What about you guys? Okay, no problem. I guess they're not here. Sahiti, Sadvedi, Pallavi, and Nikhil. One of you were there, right? Did they leave? I guess they're okay. Sadvedi, you are here. Okay, thank you. Okay, and group 8, Praneet, Vidushi. Vidushi, you were there, right? Vedavati, thank you. Vedavati, I also saw you gave a thumbs up somewhere in the middle. Yeah, Shruti, thank you. Shruti, you were also there, right? Thank you. Okay, Sindhura, you are here. Thank you. Shruti and Shivani, I guess, then are not here. Okay, no worries. Okay, so we are all on the same page. People have been able to follow, and some of you, I hope, have been able to execute up to this point. Okay, for those of you who haven't yet, please try this at home during your free time, whenever you get some free time. Okay, so let us actually see how far we have come. It is still fitting the hyperparameters. Okay, let's actually see. Just give it a couple of more minutes and check this out when this is done. Okay, so as you can see, guys, randomized search CV, the one that is only checking 20 random combinations, is taking up so much time, right? So now just imagine how much time grid search CV would take up. Okay, so these are time taking processes. Okay, so let this run. Let's see what we get. Okay, once this runs, I will show you guys again. Okay. Okay, so as you all can see, the model has finished running, right? So we can now go ahead and see which are our best parameters. Okay, let's go ahead and print that. So these are the best parameters that came up out of all the 20 random combinations that random forest tried. So which is n estimate as 300, min sample split as 10, min samples leaf as 2, max features to be used for each decision step as log 2 of the whole feature set, obviously, max depth as 20. Okay, so now let us actually get the best model that we want using the best estimator definition, and you see this is exactly what it is doing, right? It has simply defined it as how we would define it normally, right? It is simply that, as you can see, this is exactly how we would define it normally, right? So this is what that is, right? We can also print the OOV score of the best model, which is 0.76. Not too bad, it is decent. Now let's go ahead and make some predictions, right? And we have made the predictions with respect to the hyperparameters. Now let's see accuracy, somewhat better, right? So this has done somewhat better with respect to the previous one. Okay, we are not making as many errors now, only 38 mistakes. Accuracy is also not too bad, it's 75%, right? Previously it was around 72, right? So this is 75. So hyperparameter tuning actually worked, and hyperparameter tuning actually helped us gain 3% more accuracy. Okay, so that is, although that is not a lot of increase, right, that is still some increase. Okay, and a lot of the times also these things matter where the data sets are not that very clean or that good, right? If you guys remember, for this particular data set, which is diabetes, right, uh, this data set is not the cleanest, right? It has major class imbalances, it has a lot of outliers. So if you actually go ahead and try those things, right, if you try removing these outliers and if you try fixing the class imbalance, right, you might actually end up boosting this accuracy a lot more using models like random forest. So that is something that I will set as a homework for you guys. Whenever you find some time, right, you already have all the necessary scripts. Whenever you find some time, perform outlier removal or class imbalance fix, or both of them together, whichever you want, right? You can perform whatever you want and try out different things, experiment with different things, and see if that is actually giving you a better working model. Okay, so that is something that I want all of you to try, because in doing so you will also would have practiced some Python coding, and that can only be of help to you guys. Okay, so go ahead, play around with all of these scripts. It is not necessary for you to only work on the script that has been given that day, right, that has been given on that day. Work with other scripts, combine elements from the previous scripts with this script, basically play around with it. Do whatever you want to actually see if this actually boosts your accuracy, because that is the entire goal finally, right? You want a model that is highly accurate, very precise, right? That is the goal. Okay, um, I will not go ahead and execute this grid search CV part. It is the same as randomized search CV. It's just that this definition has changed, right? Here the only other parameter that you see is n jobs, which is nothing but the number of CPU cores you want grid search CV to use for this particular execution, right? I have set it to -1, which basically denotes that please use the maximum number of cores which are available to you. Okay, so this will kind of speed up the process for you if you want to run it. But then again, you guys already saw how long it took for randomized search CV with only 20 possible combinations. This guy will have several possible combinations here, so I don't think we should run this in class, but do run this part, right, by yourself, right? You can run this and leave it. It'll take maybe 10 minutes, 12 minutes, I don't know, probably. And you can come back after 10 or 12 minutes and check whether the outputs are there, and check out whether the actual best parameters are better than randomized search CV or not. Okay, maybe randomized search CV missed something, that is absolutely possible. So go ahead and try this out as well. If we do it in class, it'll take up a lot of time, so we don't need to really do this. Okay, and as a general rule of thumb, if you are using a laptop and you are not so sure about that your laptop has very high specs, then I would suggest don't even try this. Okay, I don't want you guys to crash your laptop, but still, for the sake of learning, if you want to try it out, do it, but make sure your documents and all pages, folders, etc. are already saved somewhere so that you don't lose out on any progress. Okay, with that, we will stop the execution here, and we have come to the end of another lecture on our machine learning series. So today's lecture was all about random forest, its theory, its practical, and how we actually perform hyperparameter tuning. Okay, hyperparameter tuning can be performed not only on random forest but also on every other model and algorithm that we have seen till now and we will see after this. Okay, So it is not confined to only random forest. Don't feel like I have shown hyperparameter tuning during random forest means we can only perform hyperparameter tuning on random forest. That is not the case. Okay, you can do it everywhere in every model. Okay, with that said, if anybody has any questions, please raise your hand. Otherwise, please give me a thumbs up. Okay, so most of you, quite a few of you have given us a thumbs up. Then I am assuming that you guys don't have any questions as of now. Please work on the scripts and come to me with doubts on the Telegram channel. I'll be more than happy to help you out. Okay. With that said, thank you for joining us. Bhavani, you can take over.